consider m comma n belongs to natural number, m not equal to n, m and n are not square free. Sorry, m and n are not perfect squares. Perfect squares. Perfect squares means like 2 square is 4. So 4, 9, 16, 25, 36, these numbers we call perfect squares. So we take two positive integers which are not perfect square. Then you can, then we look at f1 equal to q of root m, f2 equal to q of root n. Okay. Now we take not perfect squares. If m is a perfect square, then square root of perfect square will be an integer. So q adjoined by an integer is again q only. Okay, so we don't want that. So we take non-perfect squares. Now we claim that the field f1 and f2 are not isomorphic. Again, so for example, in the previous year question, you might have seen q of root 2 and q of root 3 are isomorphic as field, isomorphic as vector spaces. This question is there. We are solving that problem now. We are doing again for arbitrary integers. Even for arbitrary perfect squares, that result is true. Okay. So again, as field, they are not isomorphic. Okay. But f1 is, the field f1 is isomorphic to f2 as q vector spaces. So let's see why. Because element of f1 is of the form set of all a plus b root 2 such that a comma b belongs to q. Okay, and f2 elements is belongs to sorry, I think I should write m here, set of all a plus b root n such that a comma b belongs to q. Okay, so f1 is a field of characteristic 0, therefore f1 will contain q. f2 is the field of characteristic 0, therefore f2 will contain q. Now f1 is a field extension of q, f2 is a field extension of q. If f1 is a field extension of another field, then this can be thought of as a vector space over this smaller field. For example, like C is a vector space over R. Because like C is a field containing, C is a field extension of R for similar reason, or you can just check that f1 it's indeed a vector space. Okay. Okay, now if you noticed, dimension of f1, the vector space f1 over q is 2 because 1 comma root term is a basis. You see, every element of f1 is a linear combination of 1 and the root term. So a times 1 and b times root term. Similarly, dimension of f2 over q is also 2. Dimension of the vector space over q equal to 2 because again 1 comma root 10, this set is a basis. Now we know that any two vector space of same dimension are isomorphic. Therefore, f1 isomorphic to f2 as q vector spaces. Q vector spaces means vector spaces over the field q. But now we claim that they are not isomorphic as field. Claim f1 is not isomorphic to f2 as field. Okay. So first we prove a lemma. Let sigma be an isomorphism between the fields f1 and f2. Okay. We assume that characteristic of f1 equal to characteristic of f2. So if they have the same characteristic, then they have the same primes of field. Okay. Or they have the isomorphic primes of field. Okay. So in our previous video, we talked about primes of field. If the characteristic is P, then ZP will be a subfield of both F1 and F2. That is what we call a prime subfield. If both the characteristic of F1 and F2 is 0, then Q, the rational numbers, will be a subfield of both F1 and F2. Okay. Okay. So we want the same prime subfield, so we assume the characteristic is equal. Now I consider a polynomial over the prime subfield f0. Okay. Now this lemma says that if alpha belongs to f1 is a root of f of x, then its image of alpha under the isomorphism sigma is also a root of the polynomial f of x. Okay, so I hope you understand the problem clearly. You take an element here that is a root of this polynomial, then it's look at the image will be a point of f2, that is also a root of this polynomial. So let's see why it is so we have f naught is contained in f1, again f naught is contained in f2 because f naught is the prime subfield. Since f1 and f2 have the same characteristic, f naught will be subset of both the fields. Let f of x belongs to f naught of x. I take f of x to be a naught a1 x plus etc a n x power n. So let alpha belongs to f1 be a root of f of x. So these are the assumptions given. We claim that sigma of alpha belongs to f is also a root of the polynomial f of x. So we claim that f of sigma of alpha equal to 0. So what is f of sigma of alpha? Wherever x you have, you have to substitute sigma of alpha. So wherever x you have in f of x, you have to substitute sigma of alpha. So f of sigma of alpha equal to a naught plus a1 sigma of alpha plus etc. a n sigma of alpha whole power n. But sigma of alpha whole power n equal to sigma of alpha power n. Sigma of alpha square equal to sigma of alpha whole square because sigma respects the multiplication. Okay, so we can take the powers inside. Now we have all the coefficients. Now f is a polynomial over the prime field f naught. Okay, in the previous video we proved that sigma of x equal to x for all x belongs to f naught. Okay, where f is a prime subfield. Okay, this is the result we proved. Therefore, whenever you have a point in f naught, you can replace a naught by sigma of a naught because every automorphism fixes the point of the fixed prime subfield. Okay, so f naught is what we call prime subfield. So if you haven't watched the first video, now this may not make sense to you. So first to watch the first video, then you watch this problem. Okay, so a naught, a1, everything belongs to the prime field f naught. So sigma fix all the points of f naught. So a naught we can replace by sigma of a naught. A1 we can replace by sigma of a1. So we got sigma of a naught, sigma of a1, sigma of alpha, and sigma of a n, sigma of alpha power n. Okay. So now sigma is a field automorphism. So you can take sigma outside. Sigma of a1 into sigma of alpha equal to sigma of a1 times alpha. Okay. Now sigma of a naught plus a1 equal to sigma of a naught plus sigma of a1. So using these two results, you can take sigma outside, you get sigma of a naught plus a1 alpha plus etc. an alpha power n. But this is what? This is f of alpha. The element alpha evaluated at the polynomial f. But the alpha is a root of the polynomial f, so you get 0. But sigma of 0, we get 0. Okay. Therefore, what we just show is you have two field f1 and f2. They have the same characteristic. Therefore, they both have the same prime subfield. If you take a polynomial f of x over this prime subfield f naught and alpha belongs to f1 is a root of this polynomial f of x, and from f1 to f2 you have an isomorphism sigma, then sigma of alpha belongs to f sigma of alpha sigma of alpha belongs to f2 is also a root of this polynomial f of x. That's what we prove. Now using this result we claim that q of root m and q of root n are we saw them, they are isomorphic or not isomorphic. We saw them, they are isomorphic as fields. We claim that they are not isomorphic as we saw them, they are isomorphic as vector spaces. Now we claim that they are not isomorphic as field. Okay, we take suppose they are isomorphic. You take isomorphism. Now q of root m and q of root n both have characteristics 0. Okay, therefore it satisfies the hypothesis of the lemma we just proved. Now we have q of root m and q of root n both have the same prime subfield, that is q. Okay. Now we consider this polynomial x square minus m. Okay, so this is a polynomial over q. For this polynomial, root term is a root of this polynomial. Since sigma is an isomorphism between the fields from the field q of root m to q of root n, we conclude that the image of root m in the field q of root n, that is sigma of root m belongs to f2, is also a root of this polynomial x square minus m. See, x square minus m has only two roots. One is root m, another is minus root m. Therefore, we conclude that sigma of m, sigma of root m equal to plus root m or minus root m. Okay, but these two numbers, both of them are not element of q of root n. Why? Because in q of root n, every element is of the form a plus b root n. Okay, and n and m are distinct. In the problem, we took n and m are distinct square free numbers. That's what we took. See, you see, distinct square free numbers. Therefore, we conclude that root m or minus root m, they cannot be element of q of root n. So, therefore, such a isomorphism does not exist. Okay, so it is a very simple argument. This lemma is very important lemma. Okay, sorry, where is the statement? This lemma seems very long, but it is very easy to understand. You try to understand through this picture, then you can understand easily. And so we conclude that q of root m and q of root n, they are isomorphic as vector spaces. They are isomorphic, but they are not isomorphic as fields. Okay, guys. So if you like this video, please like it and please subscribe me to the channel.